Alright, so we now start the next section, having seen the summations on infinite sets in the previous one. This section now deals with uncountable sets. We already know what uncountable sets are because we know what countable sets are. So countable sets are either finite sets or countably infinite sets. So if a set is neither of these two types, then it is called uncountable. So in this section we are going to ultimately prove that the set of real numbers is uncountable. But before we get to that, there are some other things. So let us first see this result, Cantor's theorem. So what Cantor's theorem says is that if X is any arbitrary set, finite, infinite, anything, then X and its power set cannot have the same cardinality. We already know what the power set of X is. It is the collection of all subsets of X. And it's a consequence of the axiom of power set that this collection itself is actually a set. Okay, so let's see how this can be proved. The proof you can imagine, of course, is by contradiction, by the method of contradiction. Suppose there is a bijection f from X onto the power set of X. That just simply means that X and its power set have the same cardinality, by definition of having same cardinality. Consider the following set A, where A is the set of those elements X in X such that X does not belong to the image of X under F, that is, X does not belong to F of X. Now let us first see what this even means. At once it looks a bit strange. X is not an element of F of X. But it makes sense because you see, F is a function whose inputs are elements of X and the outputs are subsets of X because they lie in the power set of X. That means for any X in X, for any small x in X, F of X is actually a subset of X. And since X itself is an element of X, it's legitimate to ask whether X belongs to F of X or not. And capital A is the set of precisely those elements in X for which, which are not in their corresponding images, because the images are subsets. And you can clearly see that by the axiom of specification, this A is actually a set, and in fact, A is a subset of X. Clearly, A is a subset of X, i.e., the same thing that A is an element in the power set of X. Now, since F is a bijection, F is a surjection also, it's an onto function. Since F is a bijection, so this A being an element in the range will be an output of F for some input. Since F is a bijection, A is equal to f of, well, we are treating x as a general element, so let's take y for some y in x. You realize that this is a consequence of f being surjective, that means onto. Okay. Now a question can be raised. Why, since y is an element of x, so we can ask whether y is an element of f of y or not, that is whether y belongs to A or not. Let's see what happens if we try to answer that question. If we assume that y belongs to A, then by the definition of A, which is this, then you see y is in A means y is in x, which is of course true, but this condition should also be true for y. So the condition is this, but f of y is nothing but A. So that means our supposition that y belongs to A has led us to the conclusion that y does not belong to A. This cannot be the case. This is impossible. On the other hand, if y does not belong to A, then obviously y does not belong to f of y, because A is f of y. But then y is an element in x which satisfies this condition. So again, by the definition of A, y would then have to be in A. So by the definition of A, y must be an element in A, which again is impossible. By the definition of A again, y belongs to A. Okay, so on the other hand, this hypothesis leads us to that conclusion, which is exactly its negation. This is not possible either. So that means something must have gone wrong, and the only thing that has gone wrong is our blind supposition in the beginning of the proof that there is one such bijection. So no such bijection if exists. Thus, x and its power set cannot have equal cardinality. Now this result is of course a significant result because it is very strange, and you can see that it's Well, if x is finite, then you can pretty much understand why this happens. If you look at a few examples, you will see that as x increases in size, in cardinality, being finite, it can be quite large. 2 to the power x, if I call it like that, or rather I should perhaps say the power set of x is even more, it's larger, much larger than x, and this gap between their sizes increases drastically as the size of x increases. It is somewhat like the relationship between a positive integer n and the positive integer 2 to the power n. In fact, if the cardinality of x is n, then the cardinality of its power set is 2 to the power n, and that's why we have this notation. So as n increases, so does 2 to the power n, but the gap itself increases as n increases very rapidly. Okay, so from that you can pretty much understand that a bijection is not possible. But the significant thing here is that even when x is infinite, then also bijection is not possible. Now after this there is a remark. Let me just write, I can say it also, but still let's just see what the author has written. The remark is this: the reader should compare so you can see, or this proof must have reminded you of something. We have come across a similar situation when we discussed Russell's paradox, that is, something happening and at the same time it's not happening. So that's why the author is saying the reader should compare the proof of theorem 831 with Cantor's theorem, same thing, with the statement of Russell's paradox. Which we left behind in section 3.2. The point is that a bijection between x and 2 to the power x, if it existed, it would bring us dangerously close to the concept of a set containing itself. X and its power set. What's the language exactly? Would come. Okay, so okay, fine. to a set containing itself as an element, which we have already proved in one of the exercises at the end of that section, where we dealt with Russell's paradox, that if A is any set, then A is not an element of A. This we actually proved from the axiom of regularity, I think that is called, if I am remembering correctly. But anyway, so now let us see the next consequence of this theorem, corollary. Oh, okay. This is item number 3. That was 2. So the corollary is, the statement is just simple. The power set of the set of natural numbers is uncountable. So this provides us with a concrete example of an uncountable set for the first time. Okay, we have been mentioning that the real numbers form an uncountable set, but we haven't proved anything like that before this point. So now we are going to show that this particular set is not countable. And in this is not solution, this is the proof. And in doing so, we are going to use our Cantor's theorem. So Cantor's theorem immediately says what? It states that there is no bijection between the set of natural numbers and its power set, which is this. By Cantor's theorem, well, we can write it directly, but let's just write about the bijection. There is no bijection between the set of natural numbers and its power set. Before Cantor developed these ideas of sets having equal cardinality, or before he developed this theory of bijection and everything, people thought that uncountable sets do not exist. But he showed, of course, that the real numbers are uncountable. And his ideas were vigorously opposed. Particularly, Henry Poincaré opposed his ideas of these infinities of different sizes, but David Hilbert supported him. The later part of Cantor's life is very tragic. If you want, you can see what happened to him. But anyway, let's just go on with the proof. So by Cantor's theorem, there is no bijection between these two sets, which means what? You see, by definition, a set is countable if there is a bijection between that set and this set. Now here we have the statement that there is no bijection between n and its power set. That means the power set cannot be countable. So, is not countable. Not countable means what? That it can be any of the other two types. Either it is uncountable or it is finite. You see, there are exactly two possibilities, right? Either a set is finite, or if it is not, then by definition it's infinite. And among infinite sets, we have countable sets. And those that are not countable either are called uncountable. So now we have exactly two possibilities. This implies this is either finite or uncountable. Always keep the definitions straight, okay, do not get confused. Uncountable by definition means not countable, neither countable nor finite, okay. If I be precise, then uncountable means neither countable nor finite. It's a special type of infinite sets. But actually this is not finite, which will make us conclude that it's uncountable. But why is it not finite? Let's now see. Note that there is a natural bijection between this set the set of all singleton subsets of natural numbers and the set of natural numbers. I think you can guess what the bijection is. The bijection associates any natural number to the corresponding singleton set. Let me just keep this in within parentheses. So this tells us what? It tells us that this set cannot be finite, it must be infinite. Hence, this is infinite. But this set is a subset of the power set of n. Since this set is a subset of the power set of n, it follows from I wrote from. It follows from the properties of finite sets, and that thing was proposition 3614. That this is infinite. Well, but how? Right, we understand here that because of this bijection between this set and n, this is an infinite set. And we also understand that this is a subset of the power set of n. By the way, why is that so? That's because every element in this set is a subset of n, a singleton subset, but a subset of term. So that means every such singleton set is an element in this. So that's why this is a subset of this. Now by proposition 3614, in fact it has those many parts. One of them is being used here. One of them says that a subset of a finite set must itself be finite. So had the power set been finite, this would have been finite by that proposition, but it is not. So that means the power set cannot be finite, so it's infinite by definition. So now we can rule out the finite possibility. So that means the power set must be uncountable. That's the only option left to us. Hence, this is uncountable. And using this, we are going to show that the set of real numbers itself is uncountable, but not in this video, next week. So I am ending the video here itself, but before I end things actually, let me just tell you briefly what we are going to do next. Next is that result that the set of real numbers is uncountable, where we are going to use uncountability of this. Okay, and in the proof we are going to use series on or summation on infinite sets from the previous section. That's why we developed those things so much, that is those summations, their absolute convergence, that those ideas we are going to use in this proof. And this proof will be rigorous. You may of course be familiar with another proof of uncountability of the reals, which uses the fact that real numbers can be expressed in using decimal system. And then Cantor's diagonal argument, it's called, is used to quickly conclude that the real numbers are uncountable. However, because we are doing things absolutely rigorously, and because it takes quite a bit of effort to prove the fact that real numbers have decimal representations, so if one wants to take that route, then that is actually quite long. You may remember that in this text the author has mentioned somewhere, we have already come across it, that the fact that real numbers can be expressed in as decimals or in binary system or in some other system with some other base, these things actually have nothing to do with analysis. They are just some systems which help us write the things in symbols. Okay, there are many different systems. For example, binary system is used, which corresponds with switches being on and off in an electronic circuit, which is useful in electronic devices. But decimals are useful for us for normal purposes, where the base is 10 because we have 10 fingers. There are other systems, octal, hexadecimal, but the fact that you can express the real numbers in any of these systems, that has nothing to do with analysis. Okay, so we have taken this route to prove that the real numbers form an uncountable set. And whatever we have done so far is rigorous. And keep in mind, everything is stemming from those axioms of set theory, that is ZFC or ZFC, where you have the axiom of choice also, and the other axioms that we have so far seen. That is the base level. From there, everything is being proved. Okay, so there is no gap in our understanding. But in that proof, which is readily available anywhere, of real numbers uncountability, which is Cantor's diagonal argument, that proof uses the fact that decimal representations of real numbers exist. Okay, but that fact itself is not very elementary. So we will see how we can use summations on infinite sets to substantiate this very important result about real numbers, but next Sunday. So our next upload is this coming Tuesday, of course, and this Tuesday let's go back to field theory. Okay, so with that, see you on Tuesday. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.